Hello, knowledge seekers. Welcome to Remedial Tutorial Academy. In this video, we will see the well-ordering principle. This one's is crafted a little bit differently. So let me first define what a well-ordered set is. So first of all, let S be a partially ordered set. We will properly define this later on. Basically, it just means that if we have elements X and Y, we can decide if X is less than or equal to Y. We'll define what that is more properly later on, but we've probably seen something like this before. We say that a set is well-ordered if every non-empty subset contains a least element. So if you take any subset of the set, there's always a smallest element inside that set. The natural numbers are a well-ordered set, and so this is called the well-ordering principle. The set of natural numbers is well-ordered. If you take any subset of natural numbers that's not empty, there always will be a smallest natural number inside of that set. It turns out that the well-ordering principle is equivalent to the induction axiom. The natural numbers, in fact, is the canonical example of a well-ordered set. Well-ordered sets are trying to generalize this principle for the natural numbers, and the well-ordering principle is equivalent to the induction hypothesis on the natural numbers. Now, when I talk about the well-ordering principle for the natural numbers, that is not the same thing as the well-ordering principle for the real numbers. The well-ordered principle in that context is actually, for the real numbers, is equivalent to the axiom of choice, which is a much, much deeper mathematical topic that I'm not talking about right here. The well-ordered principle of the natural numbers is actually just the induction hypothesis. I'm sorry, the induction principle. And this can be the equivalence of the well-ordering principle. The induction principle is really just by showing a statement is true by induction if and only if it is true by looking at the smallest counterexample argument. So what do I mean by the smallest counterexample? Smallest counterexample, we'll do a proof of this in just a second. So this is a proof by contradiction, in which case you're like, if a statement is true for all natural numbers, let's prove this by contradiction. All right, let's assume this statement's not true for all natural numbers. Well, by the well-ordering principle, if the statement is not true for some natural numbers, there's a smallest natural number where that statement is not true. So the smallest counterexample. Okay, the well-ordering principle gives us that. And then you argue that taking your smallest counterexample, that its predecessor as a natural number is also a counterexample, thus violating that we have the smallest counterexample present. And so you can argue, logically speaking, that this well-ordering principle is equivalent to the induction argument, the deduction proofs we did earlier, by showing that a smallest counterexample proof is essentially the same argument, just in a slightly different direction. So if you're ever asked to prove something by induction, you can try to prove it using the smallest counterexample. And as an example of this, let n be a positive number. Let's prove that the sum of the first n odd integers is equal to n squared. So the sum of 1 plus 3 plus 5 all the way up to 2n minus 1, that equals n squared. The sum of odd numbers adds up to be a perfect square. So we will prove this. We will prove this using we'll prove this by smallest counterexample. Let me phrase it that way, by smallest counterexample. Great. How does one do that? So then we talk about that. So like by way of contradiction, assume the statement is false. Statement is false. Okay. So then by the well-ordering principle, or WOP right here, right? By the well-ordering principle, there exists a smallest counterexample. Let's call it K. I'll call the smallest number K, such that 1 plus 3 plus 5, going all the way up to 2k minus 1, this doesn't equal k squared. All right. So we can then kind of check. So we have the smallest counterexample, right? So we can note that k doesn't equal 1, since in that situation you get 1 equals 1 squared. So the sum of odd integers from 1 to 1 is just 1, and then 1, that's equal to 1 squared. So k is not 1, because that would be sort of like that doesn't work here, right? And so then let's consider the number smaller than k, right? So note also that k minus 1 is less than k, right? And so because of that, since it's smaller than it, that implies that 1 plus 3 plus 5 all the way up to 2 times k minus 1 plus 1, minus 1 there, this is equal to k minus 1 squared. So because k minus 1 is strictly smaller than k, And that means that the statement has to be true for that one because K was the smallest situation where that actually works. And so when you actually start putting these things together, then if you were to take this statement right here, you can see that this thing is going to be equal to k minus 1 squared plus 2k minus 1. Because basically, if you take the sum of the first few terms here, which is this friend right here, that's going to equal k minus 1 squared. And then if we start working through this equation, notice if you FOIL out the k minus 1 squared, you get k squared minus 2k plus 1 plus 2k minus 1. You're going to see some
cancellation right there, right? 2k cancels to the 2k, the 1's cancel, and you're left with just k squared. And so this right here then shows that the k minus 1, basically you'd see that it's like, oh, it violates that, right? So we get a contradiction at this moment because we assumed that K was a counterexample. So this statement didn't happen, right? Equality did not hold right here, but it did. We showed that it did, right? And so we got a proof by contradiction. And so therefore the statement, the statement holds for all natural numbers. Statement holds for all n. And so you can see in this proof how similar this proof by smallest counterexample feels like an induction proof, right? Because we have an assumption, kind of like the induction hypothesis that follows because of our counterexample. That's not exactly what happens, but the fact that K is the smallest counterexample means its predecessor has the property, so we kind of get our induction hypothesis. Then we show that because this statement holds, it holds for K, which gives us a counterexample because K was the smallest counterexample. Why did we show that K couldn't equal 1? Well, the reason we showed that K couldn't equal 1 is because in our original assumption, K was supposed to be n was supposed to be a positive number. So is K minus 1 positive or negative? Well, if K is bigger than 1, then K minus 1 will be positive. So we had to kind of do this initial case to make sure that it didn't happen there, kind of like a base case. This proof by shortest smallest counterexample is very much the same proof as an induction proof. And so although this doesn't show the two techniques are logically equivalent, you can see here the similarities, and I think you can kind of imagine how the rest of it would work. Hopefully a good review. This is probably not your first exposure to induction, but we can always benefit from some more practice. We'll use induction throughout this semester in this course, right? And so feel free to use it on assignments, homework, and proofs that you yourself are doing, and we'll use it in proofs we see all the time in abstract algebra. If you liked what you saw or learned something, feel free to hit the like button. Feel free to subscribe if you want to learn some more about abstract algebra or other mathematical topics. And if any questions come up along the way while you're watching these videos, feel free to post those in the comments below. Hopefully I'll see you next time. Have a great day, everyone. Bye.